Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera semua. Kami dari kumpulan 16 bagi kursus CSF3233 Keselamatan Cyber menjalankan projek kumpulan bagi tajuk Elliptic Cryptography ECC for short. Our team members are Nabil Mukhlis S68092, Ashik Daniel S65782, Farid Ashar S64227 will be your presenter. Right into the definition, ECC is a method of securing information using mathematical curves. It uses two keys, one public and one private, to encrypt and decrypt data, having the efficiency but not lacking the strength in security with smaller keys compared to older methods that lack of trade-off, demanding resources. One might wonder why elliptic curves are used in cryptographic situations. The reason is that elliptic curves provide security equivalent to classical systems while using fewer bits. For example, it is estimated in 7 array that a key size of 4096 bits of RSA gives the same level of security as 313 bits in an elliptic curve system. This means that public implementation of elliptic curves crypto system requires small chip sizes, less power consumption, etc.
Okay, Assalamualaikum warahmatullahi wabarakatuh. I'm Ashik. I want to explain about where it apply the elliptic curve cryptography, which is the ECC, the secure. So the main thing I want to highlight is in the way it apply is the messaging, the Bitcoin, and the smart device. First, the ECC apply in very crucial in messaging app like WhatsApp, Signal, Telegram, and iMessage. So the message keep secure. Like in the WhatsApp feature, we have the encryption feature, which is end-to-end encryption. After that, the Bitcoin and crypto, the ECC protect your crypto wallet and help sign transaction. After that, in smart device IoT, smart gadget like sensor and smartwatch use ECC because it's fast and light, so it's more secure. After that, the VPN also use ECC. The mobile phone usually use ECC. The digital signature and the website HTTPS usually use ECC. After that, I want to explain about the advantage and the disadvantage of ECC, which is elliptic curve cryptography. First, the ECC requires strong security with a small key. So, you will get the strong protection with less data. After that, it's very fast. So, the process encrypting, signing, and unlocking data is very fast. So, after that, the when the use ECC is save power, so it's use less battery. So it's very compatible for phone, smartwatch, and small device. After that is ECC can works anywhere. So many system use ECC, so no big change needed. After that is disadvantage of ECC. ECC is a algorithm about the cryptography, so it's very hard to understand because it's used a complex math, so it's not easy to learn or to build the ECC correctly. After that, the ECC is easy to mess up because if you not made properly, hacker can find your weakness of your ECC. After that is the all legal issue. So ECC used to have pattern problem, but most are gone now.
Now, let's briefly explain how ECC works in general. ECC is a public key cryptographic algorithm that is based on the mathematical structure of elliptic curve on over a finite field. These curves are defined using a special equation, which is dia punya equation adalah y kuasa 2 sama dengan x kuasa 3 tambah ax tambah b mod p. This equation forms the shape of the elliptic curve, and it is used to define the set of valid points that we work with in ECC. The core idea of ECC is using a process called scalar multiplication, which is repeated addition of a point on the curve. For example, if we multiply a point G by a number D, we get another point Q on the curve. This operation is written as Q equal to D multiplied by G. In this case, D is the private key, which is a secret number chosen randomly, and G is the base point, which is publicly known, and Q is the public key. This is how the key pair is generated in ECC, which is the private number, the private key is a number, and the public key is a point on the curve that results from the multiplication. The security of ECC comes from a problem called elliptic curve discrete logarithm problem, atau ECDLP. This means that even if someone know the value of G and Q, it is extremely difficult in mathematically and computationally to figure out what is D. This is what makes ECC strong and secure even with much smaller key size than RSA. Because of this strength and efficiency, ECC is widely used in modern systems, especially those that need fast and lightweight encryption, like smartphones, smart card, and IoT devices. That's the general overview of how ECC works. In the next section, we will show the pseudocode to see this process more clearly. Alright, now moving on to section 6, we will talk about how we will talk about the pseudocode of how ECC generates a public and private key pair. This simplified algorithm represents the basic steps behind ECC key generation. It is important because this process is the foundation for encryption, digital signatures, and other ECC applications. Let's go through it step by step. Step 1, we start by selecting the elliptic curve parameters. This includes the prime numbers P, the coefficient A and B for the curve equation, and A predefined base point G on the curve. These values are usually standardized and publicly known. And for step 2, we randomly chose a private key, which a larger integer D. This value must be kept secret. And step 3, we then compute the public key by performing scalar multiplication. By performing scalar multiplication, which the equation Q equal to D multiply G. Here, Q becomes public key, and it is a point on the elliptic curve. The multiplication is done over the finite field using ECC's mathematical rules. So in summary, the input to the algorithm is the curve and base point. The secret key is randomly selected, and the output is secure key pair. D as a private key and Q is a public key. D private key, Q public key. This entire process is simple in logic but very powerful in practice because of the mathematical hardness of reversing it, which what which is what we keeps our data safe. This pseudocode help us understand how ECC establish secure more communication without sharing private information directly. In the next section, we will dive deeper into the mathematical representation of ECC to better understand how the operations work. Now we move to the section 7, where we will explain the mathematical representation behind the elliptic curve cryptography, which is ECC. ECC is based on the algebraic structure of elliptic curve over a finite field. The general form of the elliptic curve equation is used in cryptography adalah y kuasa 2 mod P sama dengan dalam kurungan x kuasa 3 tambah ax tambah b tutup kurungan mod P. Here P is a prime number which define the size of the finite field. A and B are constant that determine the shape of the curve, and xy are coordinates of a point on the curve. In ECC, we choose a specific base point called G on the curve. This point is publicly known and is part of the system parameters. Then a private key D is selected randomly. This is just a larger integer. We calculate the public key by multiplying the base point by the private key using elliptic curve rules, which is equation dia Q sama dengan D darab G. This operation is not normal multiplication. It is actually point multiplication, which involves adding the point to itself repeatedly. All the calculations in ECC happens modulo P, meaning the results are always within a fixed range. This helps keep the key size small while still maintaining high security. The challenge for an attacker is the ECDLP, elliptic curve discrete logarithm problem. If someone knows G and Q, it is mathematically very hard to find out what D is. What ECC is so that's why ECC is so strong even with smaller key sizes. To summarize, ECC depends on the mathematical difficulty of reversing point multiplication over a defined elliptic curve. This is what gives ECC its security while remaining efficient for devices with limited resources.
Hello, Assalamualaikum. I'm Ashik. I want to continue about the explanation of Java code implementation of ECC elliptic curve cryptography. So, from this code shows how two people can secretly share a key using ECC. In this example, let's say A is Messi and B is Ronaldo. So both of them want to create a shared secret without sending it directly. This is like making a secret handshake where no one else knows the pattern. So I want to share about the step-by-step breakdown of this coding. Firstly, we must add, you see that, the add boundary castle BC. This add boundary castle is an extra security toolkit to support modern cryptography like but because Java doesn't fully support ECC on its own, so we must support. So we must download the jar, the bouncy castle to run the ECC. After that, generate key for Messi. So he creates a key pair, a private key to keep secret and public key that can be shared. It is called SEP 256R1, which is a standard curve used in CCC. SEP SECP 256R1. After that, generate scale for Ronaldo. He also create his own private and public key with the same method. So Messi share a secret key. He used his own private key and Messi public key. This generate a byte array that are like a share secret. So Ronaldo also create a share key. He used his own private key and Messi public key, but he get a shared secret too. So they print the secret, the code prints out both share secret. If everything is done correctly, both secrets should mesh together, even though Messi and Ronaldo doesn't send the secret directly. So in this code, you will see the bytes to hack. This small function changes the byte array raw data into a variable hexadecimal string. Okay. So both Messi and Ronaldo generate their own keys and use other public key to calculate the same share secret. This is the magic of ECC. You can share a key without really sharing the actual key. Okay. Okay, I want to explain about how ECC works. For this slide is content about the elliptic curve equation. So the equation is y power of 2 equal to x power of 3 plus a x plus b. So point of this curve use cryptographic operation. So key operation in CC, point addition, p plus q equal to r. To add point p and q. So draw a straight line through p and q. Find the third point where the line intersect the curve. Reflect this point across the x axis to get the result r. So that is point W. 2p equal to p plus p. To double a point of p, draw a tangent line at point p. Find the second intersection point of the tangent with the curve. Reflect this point across the x-axis to get 2p. So after that, I want to explain about step by step example. Start with at point P on the curve. You see on the curve, draw a tangent at P. Tangent. Find the intersection to reflect it to get 2P. Add P and 2P to get 3P. Draw a line through 2P and P. Find the intersection and reflect it to get the 3P. Okay, so we have labeled the point P, 2P and the 3P in the image. So we have highlight the line and reflection step by step. Okay.
So onto the flow of the inputs and outputs, we start with a secure key exchange process, where we have to start with importing certain libraries and files using ECC and bouncy cancel provider. Adding bouncy cancel as the security provider, we can then implement their special algorithms to process all the formulas in the next part of our encryption, where after we have a scanner to enter the name of the ECC curve to use, we have to input them in a certain order, where SEC here means standard for efficient cryptography prime, where the P is the prime type. The 256 here means the bits, R means revision 1, and that's one of the type that they can enter. The other one is SEC with a T, which indicates a binary number instead of a prime number. And from there, we have to generate their ECC key pair for both for both Ali's Ali. In this circumstances, we call for them name Messi using curve, the curve that we just typed before. which is SECP 256 bits with version 1, where we will fetch their public key hex number and also their private key hex number. And next, to have this encryption word, we have to make sure that they can both generate ECC key pair for Abu, which in this example, we calling him Ronaldo using the curve SEC B256R1. The key here is they have to use the same curve as the one that they are referring to, because if they use a different type, then it won't work, because the fundamentals of this encryption is it has to have a matching set of curves to be even able to decrypt with the same and almost identical private and public key, where for the name Abu, or in this example we call him Ronaldo, public key hex number and private key hex number are generated via the ECC import that we have just initialized before. And after we have done generating their ECC key pair, which is the public key hex and our private key hex respectively, we have to take uh, one host, for, which is in this case Ali, who is Messi, has to generate the shared secret key, where Messi's shared secret key hex will be in hex number B2394 and etc. Should have the same secret key number with Abu Ronaldo, who's generating the shared key at same exact same number, right from the start till the last digit here. See, and uh, we have to keep in mind in this output, it didn't show how the number uh, formulate, because for this number to generate to be shared a secret key, they have to take one number from the public private key and uh, uh, um, combine it with the public key of the opposite number, which is in this example is Ronaldo. So in this case, Ali has to, if Ali wants to generate a shared key with someone else, he has to use his private key with his partner public key to generate a shared secret key, and then uh, vice versa for his partner, which is Abu in this example. Ronaldo has to combine his private key with Ali, which is in this example Messi, public key instead to generate the shared secret key. Hence, when they run the formula using the curve that we have input before, which is SECP 256 with revision 1, they will generate an exact same shared secret key hex. Uh, if this isn't done correctly, then there's a chance, and definitely they will have a different hex number when they generate the shared secret key. Even with one single difference of number, generate a different hex key altogether. So the program have to at least have two countermeasures to make sure that the one we sharing the secret key, I mean, or encryption, is the one that we wanted to send, because you have to have the same you have to use the same curve to even run the same program and get the exact equal result, which here you can see checking shared secret key equality generate and a match where the key exchange is successful. If even the curve or even the key are different, then the match is unsuccessful. Most of the time, if it doesn't work, it rarely because of a corrupted key. Most time it is because someone entered the wrong curve. Like if you accidentally enter the SECP the 256R1 for the first partner. For the second partner, you enter SECT 256R1 instead, and it would result in a different key. So from that curve, they won't even intersect with each other, which like my previous teammate have explained before. So from that, we can say uh, using ECC actually benefits and actually makes a simple line and safer method of encryption than most encryption key that we have seen before. Uh, that's pretty much I get from learning and playing with this input and output version. Because I have tried with some iteration of the curve type like SECT and maybe if I remember correctly it was Boolean or something of the Russian made I think. And it will cause there's a chance it might not work, but not because that the number is invalid. It's just that there are chances that the system cannot run because it's not supported in certain IDE or environment. Just because that we are not prepared with the correct libraries or repositories. So here are the codes which shows the input and output. And so, in conclusion, through this project, we learned about elliptic curve cryptography (EC) as a powerful method for securing digital communications. ECC use smaller keys than older systems like RSA, making it faster and more efficient, especially for devices with limited power like phones and IoT gadgets. We studied the math behind CC, like elliptic curves and point operations, down to the minute detail like the ones like the basic setup, got a choice of coordinates, arithmetic elliptic curves defined over vector prime, elliptic, Diffie-Hellman exchange, Diffie-Hellman problem, decision Diffie-Hellman problems, and the digital signal signature algorithm, and maybe some of endomorphism into what's what basically there's a lot side of elliptic cryptography uh, and the math behind ECC like dictors and point operation and saw how they help create secure keys. We also explored real-world uses like online security, digital signature, and cryptocurrencies by coding an ECC simulation in Java. We gain hands-on experience and deeper understanding of how theory turns into practice. This project show us how important strong, efficient encryption is for keeping our digital world safe. And for the experience, I say thank you on behalf of my team for your time. Thank you.